right, we're going to finish section 6.3. We had taken a look at some basic properties of exponents last time. And these were our theorems or properties that we discussed, and I kind of talked through maybe some justifications about why they work. We have two more additional facts or properties about exponentials that are helpful. A to the 0 power is equal to 1. Probably remember that one. I'm actually going to show you a proof for this one, like it's a legit proof, not just a justification. But we can actually take a to the 0 power and we can write it as a number minus itself. So I don't necessarily care what n is, but if you do n minus n, you get 0. So that might seem like an arbitrary way for me to rewrite it, but hopefully you look at it and go, well, yeah, that's true. Is it true? Good. Now, one of our properties of exponents, this is using it sort of in reverse, is that this is equal to a to the n over a to the n. Okay? That was property number 2, but sort of viewed backwards, right? Property number 2 is this one here. And if we go this direction, that's what I did. Okay? But what is anything a to the n divided by itself? 1. And we have very quickly proven that a to the 0 is equal to 1. Okay? The reason that's a proof, whereas the other ones that I did were not, is because I didn't use any arbitrary numbers. I used the arbitrary variable n, and it can represent any number. That's why it's proof. All right, we'll do one more, and I'll do a justification for this one. We had one similar to this last time. It's number 6 above. It talks about what happens when there's negative exponents. And so if we have a to the negative n, it's the same thing as 1 over a to the n. And I'm going to do another example, not example exactly, but a justification as to the why this is working by, so proof by example, which is not really a proof at all. Okay, but I'm going to show you why it works. So we're going to use the example of a to the negative 3. So I talked about last time the fact that this means that I have a to the negative 1 times 3. Right, I can break the negative 3 apart. When I have that negative 1 exponent, that tells me I'm doing a reciprocal. So it looks like this. And then I can cube the top. I can cube the bottom. And 1 cubed, of course, is 1. So I get from here to here, and it looks like this one with the 3 replacing the n. So again, I show you those things not because I'm going to ask you to show it to me back, but because if some child somewhere along the way did so to you and said, well, why does it work? You could be like, hold tight. I'll get back to you tomorrow. And you could go remember and remind yourself either by Googling at that point or looking back at notes that you still have or some other resource of why it works, and it won't be the first time you've ever seen it. Yeah,
or
Braden?
YouTube videos.
Or on YouTube videos. You can definitely YouTube and look for me when you're out of class. That's true. So fun fact, all the stuff that I do with the dossier and all that kind of stuff. So 2 years ago, who do you think my previous students were emailing to try to figure out what to do when all their Canvas classes, or when all their classes went online in the spring of 2020? I even talked to parents of kids I'd had before who were administrators or teachers as well about how to use dossier in order to record videos, because nobody knew those kinds of things because we hadn't done them yet. So it's fun stuff. All right, so what we're really going to do with these is we're going to actually utilize those theorems or properties or whatever you want to call them in order to simplify expressions. So our goal is to simplify so that we only have one of each variable. So like this has an a on top and an a on bottom. I only want one of a written down when I'm done. And then I have positive exponents, so no negative exponents. There's often more than one way to do a particular problem. So I'll show you one of the ways, and then I'll talk to you maybe about, or you could have thought of it this way, but I won't show all the options, but just so that you have an idea that you can do it more than one way. So one way to handle this is property number 2. Property number 2 says that if I have an exponent or a base with an exponent in the numerator, I can subtract the exponent's base in the denominator. So this has an a on top, which means a to the 1, and an a to the negative 3 on bottom. So I can take the 1 up here and the negative 3 and do 1 minus negative 3. Okay? You have to remember to do 1 minus negative 3, so there's 2 negatives in there. The other one's a little easier just because the exponents are both positive, so the 4 on top and the 2 on bottom. So if you think about this, then of course, you've got opposite of a negative makes it positive. So 1 minus negative 3 is the same as 1 plus 3, which gives you 4. And then b is 4 minus 2 as an exponent, which gives you 2. I have a single variable a, a single variable b, and I have positive exponents, so I'm done. Okay, that's one way of doing it. Another common way, and the next one I'm going to actually mention on this one is actually probably what my gut reaction would be if I were to see it. I don't necessarily think it's the best way of doing it, but that's how I think about it immediately, is that anytime you have a negative exponent, you can move its location. So that a to the negative 3 can be brought up to the top. Now it's a cubed on top, and then I would combine using properties after that. That's how my gut reaction is to think about it. So that's another way to think about it. All right, so on part B, what you'll notice is there's no variables. Hopefully you noticed that, no letters involved. You should also notice that the parts that are in parentheses raised to the exponents are not the same, right? The bases don't match. So anytime in these properties that we had over here, let me go to the slide that has most of them on them, where I'm combining things like properties 1 and 2 and 3 even, they're all the same base. It's all base A. So the only time I'm able to combine the exponents, right, into a single base with a single exponent is if the bases already match. And on this one, they simply don't. One is 2/5 and the other one is 4/25. So in order to be able to use any of these properties, I've got to make the bases match. Now, 4 does factor, and so does 25. In fact, they factor very nicely. How in the world do 4 and 5 factor? I'll just break it apart like that. This is weird, but that's okay. How does 4 factor? 2 and 2. And how does 5 factor? 5 and 5. And that looks conspicuously like the 2's and the 5's on the other one, right? So instead of actually thinking about it as 4 over 25, I can break it apart. So I have the 2/5 to the third, and right here I have 2/5 times 2/5, which is 2/5 squared, to the negative 6th. Okay, 2 squared is 4, 5 squared is 25. Does that make sense for everyone? That's good, because now my bases match, right? They do. Now, before I can combine the 2/5 with each of the, combine it into a single 2/5, I need to combine these two exponents next. So what am I going to do with those two exponents? I'm going to multiply them. Right. So if I multiply 2 times negative 6, what do I get? Negative 12. Now, I know that's negative 12, but it will be highly unhelpful for you right now to flip it. We're going to flip something eventually, but I wouldn't do it here. Because if you flip it, 2/5 becomes 5/2, and it no longer is the same base as the other problem, or as the other part of the problem. So we don't want to flip it right now. We do, in fact, want to combine these into a single base. So how am I going to combine the 3 and the negative 12? What property? Huh? Well, it does end up becoming a subtraction problem. I'm actually adding them. It's just that one of them is negative. So I'm adding 3 plus negative 12, right? Which becomes a subtraction problem. What is 3 plus negative 12? Yeah, negative 9. So I do have a single base now, right? There's not multiple bases in the problem that I have the ability to combine but yet haven't. But I have a negative exponent. So what am I going to have to do in order so I don't have a negative exponent? Yeah, I need to flip it. So there's a couple of ways this answer can be written at the end. One option is to simply write it like this. That's okay. The other option, if you wish, is to write it like this. And that's okay. What the problem is not asking you to do is to grab your calculator and find out what 5 to the 9th is, or 2 to the 9th. It wants you to leave it in exponential form. Any questions on that one? Okay, so let's see how we can use this a little bit when we're solving equations and inequalities. So on number 7, part A, what you'll notice on the left-hand side is, if we just sort of ignore what's over here, right, just ignore it. I thought I was using a highlighter. Ignore this. If I started the problem out with what's on just the left-hand side, it looks a lot like the previous 2 problems we worked, right? It does. That's actually how we're going to start. We're going to start by making it into a single base on the left. So, how will I combine 2 to the n and 2 to the 7? You add the 7 and the n. So I'll put n plus 7, or you can put 7 plus n. Okay, now the second thing that you need to do goes along with the last problem as well. We'd like for them all to be written, when possible, as the same base. Well, 2 can't be written any other way. It's 2, simplified as small, small as it can be. But 64 can be written differently. Now, our goal or our hope when we see it is that I'm able to write it as 2 to some power. I hope you've had experiences working with powers of 2 before, but if you haven't, it's not a big deal. You're just going to play with your calculator till you find a power that works. So you look at it and you say, hey, look, I think maybe it's 2 to the 10, and you're going to put 2 to the 10 in your calculator, and your calculator's going to be like, nope, that's too big. And you're like, okay, well, like maybe it's 2 to the 5, and your calculator's going to go, nope, that's too small. Right, and you're going to keep trying something in between until it works out, and eventually you're going to land on 2 to the 6th. Okay, 2 to the 6th is 64. Okay, your calculator will find that for you just fine. Okay, so we get this by trial and error. There's other ways to do that, but trial and error will work just fine for what we're doing. Okay, so now we have 2 to the n plus 7 on the left and 2 to the 6th on the right. And these match, right? And the whole thing here is supposed to match the whole thing here, right? So the entire left and the entire right match. The bases match. So what do you think that means for my exponents? They also have to match. So what we're really doing now is we're just boiling it down to the pieces that currently don't look like they match. N plus 7 and 6 are not the same value, just at face value, until we figure out what is n. N is -1. Exactly. Right, -1 plus 7 is 6. Is everybody good with that? Okay. Inequalities are a little different, and fractions feel a little bit different. Please remember, anytime you have a fraction where you've got 1 over a number, that you can very quickly rewrite it to the -1 power, like that. 81's easier for us to think about than 1 over 81. Okay, it's the same thing, but it's just easier to think about. So, again, on the left, I have 3, which is a prime number in its smallest form and all that good stuff. I can't break it down, but 81 I can. Now, you could do some trial and error if you wanted to, like I did on the last one. I'd like to show you one other way besides trial and error that you could do. You can take the 81 and you can break it down by factoring. Now that's a familiar enough number for you to know. 64 is 2, but you probably recognize that this is 9 times 9. 64 you would have recognized as 8 times 8. So you can break the 9 down into 3 times 3. And lo and behold, there's those 3's showing up just like on the other side of the inequality. Right? Our expectation is that something like that's going to happen. How many 3's? 4. So this is now 3 to the 4th to the -1 on the right and 3 to the n on the left. How can I simplify the part that's on the right? Yeah, the 2 exponents, right. So there's a 4 as an exponent, there's a -1 as an exponent. If I multiply them, I have -4. Now this isn't an equation, it doesn't say equals in between, but do notice the bases match, right? So those parts are actually equal, which means the exponents have to have the same less than or equal to relationship that the original inequality had. So at this point it boils down to just looking at exponents. So I've got my n on my left, I've got my -4 on the right, and I have a less than or equal to in between because the inequality was less than or equal to. Is that all right? you're going to have a few equations and inequalities. There's not a lot of them, but there are a few. All right, so examples 8, 9, and 10 are all examples of like that connections section. Yes, Abby?
You don't have to choose a number for n if it's a solve for n?
No, if it's a solve for n, you're like on the first one where it said equals, you're going to get a value for n. On the second one though, since it said less than or equal to, means you're going to get a range of values, so your answer is going to still have that less than or equal to in it. Or potentially it could change directions, right? If you multiply divide by negatives, it changes inequalities from greater than to less than or something like that. So that could happen possibly too. Yeah. All right, 8, 9, and 10 are connection questions. All right, they're different kinds of things that you might see in section C. Example number 8 talks about an approximation. There's nothing terribly difficult about this problem, but I put it on here because sometimes people aren't quite sure when we say approximate how exact you still need to be. So we're really approximating. For example, taking a look at those numbers, 20 and 1/3, 9 and 7/8. What's a nicer number than 20 and 1/3 that 20 and 1/3 is close to?
20 1/4.
Well, 20 and 1/4 is nicer, but there's better than that.
20.
How about just 20? Can we just use 20? Yeah. Whole numbers are better to work with. I mean, they're easier anyway. And what's a nicer number than 9 and 7/8 to divide 20 by? 10. Right? So this isn't exact, right? But that's not what we're asked to do. We're asked to find an approximation. So what is 20 divided by 10? It's 2. So whatever this exact answer is, it's going to be approximately 2. The reason that it's valuable, there's lots of reasons why it's valuable to know approximations. But one reason is because if you've got problems that you're actually working out, let's say that they asked you to do this problem, like actually work out this problem. And you want to know if your answer is like reasonable or not. Well, if it's not close to 2, it's not going to be right. So if you do this and you get an answer that's 20, something happened, right? You need to pause and say, okay, what did I do wrong? So just as a sort of check step at the end of a problem, being able to approximate as to what's reasonable and what's not reasonable is very helpful. Okay, we're going to do another one. We've got Jasmine. Jasmine's reading a book. She has 1/4 of the book left. And she has read 246 pages. How many pages does she have left? So more and more common with electronic versions of things, you can see how much of a percentage of a book or something, if you're reading an electronic book, you have left. But the page numbers don't always correspond. The same thing happens even when I look at this textbook that we have for this class, and I look at it inside a bookshelf, which is a resource that I have available because I'm teaching from it. It doesn't always show up on the right page. So it'll tell you like what percentage you are through the book. You're 52% through the book or something like that, but it doesn't always show you the page number. So these kinds of things can happen. We've got Jasmine. She has 1/4 of the book left, and she's read 246 pages. So it's valuable to notice that she has not read 1/4 of the book, right? She has read 3/4 of the book. Does everybody see that? If she has 1/4 left, then she's already read 3/4. Are we good with that? Okay. So she has 3/4 of the book left. So 3/4 of our book times x is going to equal our 246 pages that she has read. She's read 246, she's read 3/4. So the fractional piece over here, 3/4, represents the proportion, or the ratio rather, of the book that she's actually read the pages numbers of, which is 246 on the right. Okay, so we talked last time, actually we didn't, you watched a video that talked last time, about how we would go about solving an equation like this. What would I have to do to sort of move or to eliminate the 3/4 that's on the left? I would divide by 3/4, but dividing by fractions is a little easier to accomplish if we do what instead? Multiply by the reciprocal. So dividing by 3/4 is the same as multiplying by 4/3, the reciprocal. And of course, the goal here is that the 4/3 and the 3/4 cancel. That's our goal. That's why we used that. And then on the right, I need to figure out what is 246 times 4/3. So grab a calculator if you have one. 984, that sounds big. Is that true? I have something smaller than that. But I think that's probably the 246 times the 4. It probably needs to be divided by 3 still. 328. Yeah, it's divided by the 3, yeah. So I have 328. What does 328 answer? I mean, does it answer the question that's asked? What did I actually find? So this is my total pages. Now, is that what I was asked for? No, it wasn't what I was asked for. So it could have been what I was asked for, right? Like that's a possible question. It just wasn't the question I was asked. So the question I was asked is, how many pages does she have left? So what do? Yeah, I subtract. So my 328 minus my 246. What is 328 minus 246? 82 pages. She has 82 pages left. You guys doing okay? All right, any questions on number 9? Okay, I like 10 a lot. Let's look at 10. Number 10, we have Al. Al gives 1/2 of his marbles to Hosea, excuse me. Hosea gives 1/2 of his marbles to Isabel. Isabel gives 1/2 of her marbles to Letitia. If Letitia was given 4 marbles, how many marbles does Al have? So the reason that this is in this section, let me just say, because this looks a little bit off the wall. The reason this is in this section is because it's the idea of doing something repeatedly. Like that's what exponentials are, right? You multiply by 3 repeatedly. Well, this is multiplying by 1/2 repeatedly. Or you could say I'm dividing by 2 repeatedly. That's why it's showing up in this section, is because of that repeated nature of multiplication and or division, if you think about it that way. Now, this is a problem that could easily have shown up in number theory in section 1 of our book 1.1 as well, because that's a problem-solving chapter. So we've got Al, and then we've got him giving marbles to Hosea. And then Hosea gives marbles to Isabel. And then Isabel gives marbles to Letitia. Okay, and in the end, Letitia has 4 marbles. So let's work our way backward. Okay, Letitia's marbles were all given to her by Isabel. But how many marbles did Isabel have before she gave hers away? Not half. Double. 2 times that. So if we're going backward, it would be 2 times that. So she had 8. Okay, I mean, now she has 4. She has 4 now, because she gave her, of her 8, she gave 4 of them to Letitia. But she originally had 8 given to her. The 8 was given to her by Hosea. So how many did Hosea originally have? 16. Again, he doesn't have 16 anymore. He now has 8. Right? And then we go backward one more time to Al. Al gave 16, so he had 32. But that's not what the question asked. The question did not say how many marbles did Al start with. It could have, but it doesn't. It asks how many marbles does Al have now? 16. Why? Because he gave half of his 32 away to Hosea. So pay very close attention to the way the question's worded. Because any of those are valid questions. You just need to make sure you're answering the question that's asked. All right, any questions on that one?